All right, there we go. All right, so our topic for the day for coffee and chemicals, or actually today it's sparkling pink grapefruit, because I'm already past coffee time this morning. Coffee time started early today. The topic for today is reaction kinetics. And does anybody remember what you're talking about in general when you say kinetic or kinetics?
Particle movement.
Yeah, motion. Except in this case, it's not really the motion of the particles, it's the motion of a reactant or of a reaction. So the actual process of going from here's my reactants, and then it goes through all these steps, and then here are the products. And so when we talk about steps, every time you break a bond, that requires energy coming in. Anytime you form a bond, that releases energy. Whether something's endothermic or exothermic depends on whether or not it takes in more energy than it releases, and all these things. So every time an electron moves around, bond formed, bond broken, that's a step in that entire sequence of events from reactant to product is what we call the reaction pathway. So you literally think of it as, you start as reactants and you walk along a path and there's lots of things to stop and see along the way, and then eventually you get to where you're going. And so I've got a few slides to show you. The slides are all in the Coffee and Chemicals shared folder. I do, as always, recommend taking a few notes as we go through this, just because there is a follow-up activity with this, featuring a pretty fun crash course video today, short one that supplements this. But know that the slides that I'm going to show you are all in the shared folder. So let me kick over and get out of my Coffee and Chemicals one and get into my this one and share it. So it's okay. You can see what I'm saying. So reaction rates. Whoa, it just beeped at me. There we go. So this little concept here is very important. This is like the fundamental theory that underscores all of chemical reactions, that reactant particles must collide in an effective manner for a reaction to occur. And the guy in Crash Course does a great job of continuing the explanation of this. But basically it says that you cannot have two reactants on opposite sides of the room and expect anything to happen. The individual particles of the reactant have to come together. They have to collide, and they have to collide in the right way. If the molecules don't collide at the right speed and the right angle and all of these things, the reaction doesn't happen. So this becomes a probability question when it comes to how quickly a reaction progresses. Anything that you do to increase the probability of an effective collision, and the analogy in the other video is like cars at a demolition derby, or I also like to think of it as people on an ice skating rink. Anything that you do to potentially increase the probability of a collision is going to increase the probability of an effective collision and increase the probability of when two people at the ice rink collide that they're going to end up on their rear ends, which is the reaction actually having occurred. So this is the fundamental underpinning of all of this is collision theory. Reactants must collide in an effective manner for a reaction to occur. So again, jump in if you got a question, or you can plunk it in the chat and I hopefully will see it. But when I'm screen sharing, the chat doesn't always come up very obviously. So this scary looking equation is what covers rates of chemical reactions. Now we are not going to do any calculations with this. You really don't do calculations with this necessarily, because this value K is a very abstract value, except that, essentially, conceptually, the higher the K, the faster the reaction is occurring. So any changes you make to characteristics on this side of the reaction equation that eventually increase K, your reaction will speed up. Anything that you do over here to decrease K, the reaction slows down. And there's really three parts of this, A, EA, E sub A, which is activation energy, and then T. R is a constant. It's a balancing coefficient. E is the great base of natural logarithms. So I don't know if you guys have done those in math class yet or not. But so really the three variables we're working with are A, T, and EA. And T is the obvious one. Why do we put foods in the refrigerator? Because cooling them down slows down the chemical reactions that cause food to spoil. So lower the temperature, and because this is a negative exponent here, if you increase the temperature, so anytime you increase the number on the bottom of a fraction, that makes the overall quantity smaller. So like when you go from 1/2 to 1/4, 1/4 is a smaller quantity than 1/2. But when you make a smaller negative exponent, that has the opposite effect. A smaller negative exponent is a larger quantity. So like, 4 to the -2 is 1/16, whereas 4 to the -1 is 1/4. So 1/4 is a larger quantity than 1/16. So in a roundabout way, if you follow the mathematics of that, increasing temperature, if you snake it through this whole calculation, increases K. So when you heat something up, it speeds up the reaction. When you slow it down, and we know this, we did this with magnesium. Magnesium reacts with the oxygen in the air. We wanted it to happen very quickly and brightly, so we stuck it in the Bunsen burner, and that heated it up. And it also activated the reaction. So this other quantity, activation energy, is the amount of energy that it's going to take to start the reaction. And this is a graph that's commonly utilized to illustrate that. So the reaction pathway is the x-axis. So you start at your reactants and you finish at your products. And then the left side is a measure of energy. And don't necessarily focus on what specific type of energy it is, but just know that this is energy on the left side. So this hump that you have to get over. So you can imagine you're trying to get a ball to roll from reactants to products. You first have to push it up over the hill, and then the ball will take off and actually go. So when we took the magnesium and put it in the Bunsen burner, we were pushing the magnesium up to the top of the hill until finally, whoosh, it went down and we got a bright light and it reacted and all of that. So higher activation energy means a slower reaction rate. So if we go back to this, you're increasing the size of the negative exponent, which snakes through to be a smaller K. The higher the hill, the tougher it is to get it over. So one thing that we do is sometimes we can use substances to change the reaction pathway, and that's what catalysts do. You can't really lower the activation energy of a specific pathway, but you can perhaps give it a shortcut, and that's what catalysts do. You got to imagine that a catalyst is the bouncer at the door of a club, and they open the little side door and say, "Hey, come in here," and it's like the shortcut into the club or whatever. Why is with a catalyst on there twice? I don't know. Sorry. But so the catalyst offers the reactants a shortcut to get from start to end. So without the catalyst, the reactants have to exert all of this energy to get from point A to point B, but with the catalyst, they take a shortcut that has a lower activation energy. So the catalyst doesn't change the activation energy of the reaction. It actually gives the reactants an alternative reaction, an alternative pathway to produce the same products. The opposite of a catalyst is an inhibitor, and inhibitors do increase the activation energy. They stand in the way of that energy being transferred to the particles in order to get them to react effectively. So if you kind of, conceptually look at it, inhibitors make the hill higher, make it harder for the reaction to progress. Catalysts provide a shortcut that has a lower activation energy and allow it to progress more quickly. In these activation energy drawings, we can also see an illustration of exothermic versus endothermic reactions. When you do an Exothermic reaction, you end up having released energy. So the products are at a lower energy than the reactants. This, what we see is delta H. Remember what delta H stood for? A change in one of the E words that we studied back in melting and freezing and all of that.
Enthalpy.
Yep. So you have, it's even labeled on the axis here. Way to go. When you give up that energy, that enthalpy, that's exothermic, giving it off to the environment, so your products have less than reactants. Endothermic, it's more, and we've talked all the time about how natural systems like to proceed from high to low energy, and if you think about that, it makes no sense that an endothermic reaction would ever occur. But if you look from the top of the activation energy down toward the final product, that actually is moving from high energy to low. So the way that we can get an endothermic reaction without violating the laws of nature is it's going to take an extra push of energy to get those reactants to start. And once they start, now they're just following the natural flow of thermodynamics, which is from high energy to low energy. So it all works. But notice that the products have a higher energy than the reactants. They've taken in that delta H, which represents an endothermic reaction. There's like a dozen different ways to define endothermic and exothermic, and through enthalpy is another way to define them. So we get the rate equation: temperature, increasing rate, that direct relationship. Activation energy, increasing activation energy, decreases the rate, that inverse relationship. And the last term is this really abstract thing called the pre-exponential factor, because it comes in the equation before the exponential term. That was a really original name. But basically, that coefficient A, incorporates concepts such as contact surface area, concentration of reactants. If you can imagine, if you put more people onto the ice rink during public skating, there's a greater chance that people are going to collide. So that's increasing the concentration of reactants increases the chance of collisions, increasing the pressure, so squeezing the reactants into a smaller space, giving more surface area for the reactants to touch will also increase the reaction rate. Again, the thought process goes back to collision theory of anything you can do to increase the probability of an effective collision is ultimately going to speed up the reaction. Pretty straight. I mean, a lot of this stuff is logical, never really tied it into a scientific, mathematical, theoretical explanation, but you know, we have pretty good experience with lots of these things. And we've done some catalytic reactions. The copper and silver one was catalyzed with the nitric acid, and it allowed it to go a little more quickly than if we had just let it sit there. Thumbs up, good so far? Yes, I think I saw one, didn't see any digital ones. Okay, so I am actually gonna do a few things with this now, a couple demonstrations, and then that'll be it for today. So we're kind of running right on schedule. So the first reaction I'm going to do is a simple example of altering that pre-exponential factor in a chemical reaction. So I do need to use my gloves today. Did I not bring them over? I brought them over. Oh, there they are. So step back here, and of course we can't wrap up chemistry for the year without setting some stuff on fire. So why not? But the first reactants I'm going to use are potassium permanganate, and hopefully you remember the polyatomic group permanganate, which is MnO4, and manganese is widely known for its pretty purple color. It's one of my favorite colors in chemicals. Is the manganese purple color, and I don't know if I can show it in that camera, but you can kind of see it's a grayish purpley powder inside the jar. Reactivity rating of 3, that's always a good sign. And the other thing I'm going to use is good old glycerin, Glycerin is a common ingredient in a lot of cosmetics and lotions because it's very slippery and smoothing, but it's an organic compound, C3H5OH3. So a few hydroxyl groups on the side of that with 3 carbons. So I'm going to switch over my camera here to this one over at the fume hood. And so the first thing I'm going to do is just take a little bit of a pile of the potassium permanganate. Hold on, I'm going to move my iPad monitor over here so I can see myself. And I'm just going to take a little bit of the potassium permanganate and just pour it onto a ring stand base here. So I've done nothing with it. I've taken it straight out of the container, just a little pile of grayish purple powder there. I'm going to unscrew the top on the glycerin. This stuff is really thick, so it takes a little bit to get it up in the pipette. And I'm going to put some glycerin on the potassium permanganate. And that's really exciting. Exciting stuff. Nothing's going on. Actually, something's going on. It's just not going on very quickly. It may even take off while I'm doing this, but let's take this same reactant, same jar, and hopefully you recognize this as a mortar and pestle. And I'm going to take approximately the same amount of reactants, put it into the mortar and pestle, cap my jar of reactants, and I'm going to grind it. So there now you can see purplish color shows up a little bit better, but I have ground the reactants, and I have a big thing of scupulas over here, and I'm going to momentarily switch over to the other microphone. So the sound, I won't be quite as clear, but you'll be able to hear what's going on. So probably more echo now, and the sound of the fan on the fume, right?
Yeah, yeah.
All right. So I'm going to take it and dump it out right next to the other one. Stick it in there. Humid in the Mason lab this morning. So I'm going to keep in a pile the same as I did the other one. And get my glycerin back. Oh, it's all over the table now. So side by side, we can see that. So side by side, you can see that the reaction on the left still has done not a whole lot visible, whereas this one burst into flames, and now I have this little molten, previously molten core. It really looks like basalt, like cooled lava rock there. But so I have this product core left over from a highly exothermic reaction. So there were some things to observe there in that we started with, it still took a few moments to get going, and that was the activation energy being overcome. But as soon as that activation energy was overcome, now we had increased the contact surface area. So if I have, this is a little thought experiment you can do where if I have a box that is 1 centimeter on each side, but then I take that box and I cut it into 4 boxes, you've greatly increased the surface area that is in contact with its surroundings. So by grinding it, the larger crystals that were in the container, you grind them into a fine powder that really substantially increases the surface area. So when you put the glycerin on it, you have many more contact surfaces. Many more contact surfaces increases the probability of effective collisions. Increasing the probability of effective collisions increases the reactant rate. And because it's exothermic, once it starts to heat up, that increases the reaction rate even further, and you get this little ball of flame in the reaction of potassium permanganate and glycerin. I'm going to do one other reaction, which is probably the most fun. This is the prettiest, and it probably doesn't come over well in Zoom, but I'm just a purple kind of person, and so I always like that one, but this ends up being a real mess to clean up. So the next reaction I'm going to do involves, of all things, sugar, just sugar. We consume it all the time. We consume a lot of this. And if you have never actually taken like the amount of sugar that is in 1 bottle of soda and put it on a balance scale, like 45 grams of sugar, it ends up being quite a pile of sugar. So I'm just going to use a couple of grams of sugar, and I'm going to react that with a chlorate, specifically sodium chlorate, both white powders. And sodium chlorate, hopefully you also know the polyatomic group chlorate, which is ClO3. Sodium chlorate essentially is table salt with a bunch of oxygen stuck on the end of it. And when you hear the word chlorate, that's commonly associated with explosives. And the reason it is because anytime you want something to burn very rapidly, anything you can do to increase the oxygen supply is going to facilitate that. So you take in sugars, you breathe in oxygen, and that's a reaction that ultimately releases energy in your body. So the more rapid the oxygen intake, the more rapid the oxygen's exposed to the sugars, the more rapidly that decomposition of sugar can happen. So what's nice about, what's nice about this reaction is that the sugar and the sodium chlorate is going to break down, eventually produce table salt, carbon dioxide, and water. So the products of this reaction are very safe. However, my smoke detector in my lab doesn't like them. So the last time we did this not in the fume hood, we got to evacuate the whole building, and it happened to be right in the middle of an AP test, which went over really well. So I'm going to do this in the fume hood, and I'm going to switch over to the webcam again. There we go. And I'm going to clear my manganate stuff out of the way and bring in another plate and a mortar and pestle. And I'm going to go ahead and put some sodium chlorate into the dish. And I'm going to go ahead and put some sugar into the dish. Woohoo! I've mixed the reactants, yay! Another exciting reaction. You know what? Hey, I'm going to grind them. And I'm going to grind them together. This is not like the cartoons where they shake an explosive and it blows up. I'm grinding them, and still we have 2 white powders together, and seemingly nothing's happening. Seemingly, remember, it can be happening, we just might not see it. So I always like doing this where I say, hey, let's light a candle, but let's not use a match. So I'm going to take my reactants here, sugar and sodium chlorate, and I'm going to go ahead and put them on my candle here. And oops, it looks like I used too much. Well, what a shame. So, but I don't appear to be getting much of a reaction. So I could heat this up. This reaction is sometimes called is also done as the sacrifice of the gummy bear, where you use a gummy bear as your source of sugar. And if you heat up the chlorate and put a gummy bear into it, the gummy bear kind of explodes, which is really fun. Actually, it doesn't explode; it just burns very quickly. And in the Today in Chemistry post, I put a link to a sacrifice of the gummy bear video that is very interesting. But what's another way? So I don't have a gas jet here in the fume hood. So what's another way I could speed up the reaction? I've already ground it, can't heat it. How else could I speed up a reaction?
You could increase pressure.
Could increase pressure. I'm not quite sure I would know how to do that. Plus, pressure doesn't apply quite as much to solids and liquids as it does gases, and we have solid reactants here. How else can I speed up a reaction?
With the catalyst.
With a catalyst. And guess what? I happen to have a catalyst right here. Catalyst, 91% pure sulfuric acid, the absolute most dangerous chemical that we possess here in the science department of Boston Trinity Academy. And I just happen to have some of it standing by. So I'm only going to put a few drops on this. It doesn't take much. Remember, the catalyst doesn't participate in the reaction. It's just going to walk up to the sodium and the chlorate and say, hey, I've got a shortcut for you. So I'm going to switch over again to the other mic. Now we're back here at the fume hood of the echo again, yes? Correct?
Yeah, we can hear.
All right, I don't want to have to do this twice. All right, here we go, just a few drops of catalyst. I'm not quite sure if the candle is actually lit. Quite honestly, I'm not quite sure if the candle still exists. I don't know. Oh, still going. Yeah, the aluminum is actually melting. So, sort of still there. I'm not sure. But, so, that was maybe about 5 grams of sugar that I put into that. And so if you take that and multiply that up to the 45 grams of sugar that's in a bottle of soda, that's a lot of energy that can potentially come out of that. So, you know, plants do a wonderful job. They take sunlight, which is a tremendous energy source, and they synthesize these sugar molecules that really are just, you know, packing in the energy. And our digestive systems, for us taking in oxygen and sugars, break that down. Obviously, they don't release it all at once. It's released more slowly over time. But in this case, by supercharging the environment with a lot of oxygen, that oxygen just snapping off of the sodium chlorate, then we get it released all at once. So the dark char that's on there is some leftover carbon, but the overall reaction products of what you were seeing are salt, table salt, sodium chloride, carbon dioxide, and water. And it's kind of still burning. I'm not quite sure how long that's going to burn over there, but good thing I did it in the fume hood. So we basically touched on every one of the components of the Arrhenius equation. We discussed how we ground the reactants with the potassium permanganate, which sped up the reaction. And as that exothermic reaction progressed, the increased heat accelerated the reaction even more. We had another reaction that we could have done by heating it, but given the lack of a heat source, we went ahead and used a catalyst, sulfuric acid, which is a very common catalyst, to speed up the reaction. And it just, I'm gonna go close the fume hood because it just kind of exploded over here. But anyway, so that is my presentation for today, the last coffee and chemicals of the year, which is ending in a still spectacular ball of fire over here. And why should it end any other way? So I'm going to go ahead and stop the recording here in a moment. Don't forget, there is a follow-up activity posted on the Today in Chemistry post. It's a short Google form worksheet with the crash course video, and also I've posted, it's still going. I posted a link to the official sacrifice of the gummy bear video, which is a slightly altered version of the experiment that I just did.